Hey everyone, it is June 17th, 2026, and welcome to today's deep dive. We're looking at dev trends on the go, specifically today's Qiita picks, which is perfect for your commute.
Yeah, and for those listening from outside the Japanese tech scene, Qiita is basically Japan's most popular knowledge-sharing platform for software engineers.
Right.
You can think of it as the Japanese developer community's equivalent of Dev.to or Medium.
Exactly. And our mission today is looking at this recurring theme across a bunch of these trending articles, which is counterintuitive discoveries in modern coding. You know, those moments when the obvious answer just turns out to be completely backwards?
Which is, remarkably common in software
Yes,
engineering. We
totally.
constantly build these mental models of how systems should work, right? Like configuring AI hardware or micro-optimizing a function or just our daily habits. And frequently, the tech is just evolved in a way that makes our assumptions totally obsolete. But real quick, before we jump into the articles, if you're enjoying the show, please hit subscribe and like. We've got new trends for you every single day.
Yeah, please do. Okay, so starting off, there's this very specific kind of frustration developers face. It's that feeling of spending hours trying to outsmart a system only to realize you kind of played yourself.
The classic over-engineering trap.
Right. It's like, think about being stuck in rush hour traffic. You decide to take that secret, winding dirt road you found on a map just to beat the congestion. You're dodging potholes, navigating around a tractor, and you finally merge back onto the highway.
And you look over, and it's the exact same blue sedan that was next to you before you got off.
Yes, exactly. You did all this manual labor and mental gymnastics only to arrive at the exact same time.
We just have this deep desire to believe our manual cleverness can beat the established infrastructure.
We really do. And our first article from Qiita captures this perfectly. So this developer went on a 12-hour weekend quest to optimize a text checker.
Right, and for context here, in Japanese applications, you frequently need to validate input by separating half-width characters, like standard Latin letters, or half-width katakana from full-width characters, like kanji.
Yeah, and the standard approach for that validation is using regular expressions, or regex. But this developer just hated the computational overhead of regex.
Which is fair, because a lot of developers view regex engines as inherently heavy. The engine has to spin up a state machine, parse the string, match specific patterns.
It's a lot of work.
It is. When you're processing millions of characters a second, that abstraction layer feels like this obvious bottleneck just waiting to be optimized.
So the developer completely bypassed regex. They rewrote the entire check using these highly complex bitwise operations.
Wow. Bare metal.
Yeah, literally down to the bare metal, directly checking the raw ones and zeros of the Unicode character boundaries. And at first, it looked like a massive victory. They benchmarked it, and the bitwise code sped up the processing by 3.1 times.
Oh, wow.
Yeah, it dropped from 222 milliseconds down to 71 milliseconds for 10 million loops.
See, achieving a 3.1x speedup is exactly the validation you're looking for when you take the time to write manual bitwise operations. It justifies all that unreadable complexity.
Right. But here comes the heartbreak. During the final phase of testing, they decided to benchmark their highly complex bitwise masterpiece against just a standard, simple mathematical comparison.
You mean just using greater than and less than signs?
Exactly, just checking the character codes with basic math. And the simple code ran in 70 milliseconds.
Oh, no.
It was actually 1 millisecond faster than the 12-hour bitwise optimization.
That is brutal. But it reveals a critical truth about modern just-in-time compilation.
So you mean the compiler just fixed it for them?
Basically, yeah. The V8JIT compiler, which powers Node.js and Chrome, is just remarkably sophisticated now. Like a decade ago, manual bitwise operations would have given you a tangible boost.
But not anymore.
Not anymore. Today, the V8 engine actively monitors hot code paths. So when it sees simple greater than and less than checks running millions of times, it speculative optimizes them directly into highly efficient machine code. The engine is effectively performing the bitwise optimization for you on the fly.
So it's literally like building that secret dirt road, only to realize the city just paved a superhighway right under your nose.
Exactly.
And the irony goes even deeper. The developer eventually realized the widely used regex snippet they were trying to beat in the first place had a silent bug.
Wait, really?
Yeah. It was checking the hex range A1 through DF, and it was catching Latin 1 supplementary characters, but completely failing to catch the half-width Japanese katakana they actually needed.
Which is wild. It just shows that trusting the compiler is often vastly superior for writing unreadable, quote-unquote, clever code.
Yeah, the mental overhead just isn't worth it.
Exactly. Maintaining manual bitwise logic, plus the risk of edge case bugs. It's not worth the effort when the runtime environment already optimizes standard operations flawlessly. Who is this really useful for? Honestly, any front-end or back-end developer obsessed with micro-optimizing JavaScript, let the engine do its job.
Right. So if software compilation is actively negating our optimization attempts, the hardware side of the equation is equally counterintuitive.
Ooh, hardware optimization is a whole different beast.
Yeah, so we have this piece about a developer trying to run a massive 35 billion parameter AI model, the Qwen 35B model, on a standard consumer graphics card. An RTX 4070 with only 12 gigabytes of VRAM.
Which, just on paper, shouldn't work. A 35 billion parameter model, even when heavily quantized or compressed, usually demands upward of 20 gigabytes of VRAM just to load the weights. Fitting it onto a 12 gigabyte card implies severe performance compromises.
Right, so the developer initially used Llama's auto-split feature, which follows standard logic, right? Push as much of the model onto the fast GPU as possible.
Because the GPU is built for parallel processing.
Exactly. So it loaded about 42% of the model onto the graphics card and spilled the rest into the system's standard CPU RAM. But the output was sluggish, like 12 tokens per second, which feels terribly slow for a chat interface.
Yeah, that's not a great user experience.
So to fix this, they used a tool called llama.cpp and forced a hardware override. They evicted all of the model's experts off the fast GPU and pushed them onto the slower CPU. They only kept the attention mechanism and the KV cache on the GPU, and the generation speed immediately tripled to 34.6 tokens per second.
Wow.
But wait, hold on. That makes zero sense based on basic hardware principles.
It sounds totally backwards.
Right. The GPU is the sports car. The CPU is a minivan. Why would evicting the core AI components to slower hardware cause the speed to triple?
So the answer lies in the specific architecture of the Qwen model. It uses a mixture of experts, or MOE, design.
MOE, right.
Yeah. Even though the model has 35 billion parameters, it is highly sparse, meaning for any single token of text it generates, only about 3.3 billion parameters are actually active.
Oh, I see.
The remaining parameters, the other experts, are completely dormant. They're just sitting there waiting for a prompt that requires their specific domain knowledge.
Oh, okay. It operates like a giant corporate department, but only a few people are actually typing at their desks at any given millisecond.
Precisely. Now, factor in the components left on the GPU. The developer kept the attention mechanism and the KV cache.
And what's the KV cache again? Just plain English?
The key value cache is essentially the model's short-term memory. It stores the context of the previous tokens, so the AI doesn't have to recompute the entire conversation history for every new word.
Right, that makes sense.
And both the attention mechanism and the KV cache are intensely bound by memory bandwidth. They require data to be read and written at blistering speeds. GPU VRAM provides that massive bandwidth.
Okay, I'm tracking.
But by cramming 11 gigabytes of dormant, inactive experts into a 12 gigabyte GPU, the developer was consuming all the physical space. The attention mechanism was being starved of the bandwidth it desperately needed to operate.
So by evicting the dormant experts to the CPU, you're basically clearing out the VIP lounge so the attention mechanism actually has the room to do its job.
Exactly. Freeing up memory bandwidth for the operations that actually demand it is vastly more important than blindly hoarding GPU compute power. It's really a masterclass for AI tinkerers in understanding the physical bottlenecks of your hardware rather than just rely on the default configuration.
So, knowing that developers are figuring out how to run these incredibly powerful models locally on consumer hardware, it kind of forces us to look at the next logical step.
Which is deploying them safely at work.
Right. Moving from a personal sandbox to an enterprise network introduces intense security variables.
The threat landscape just changes immediately. Our sources break down enterprise AI security into 3 distinct levels. Level 1 involves basic API usage with generic prompts.
Already standard.
Level 2 requires strict content exclusion policies. And Level 3 demands fully air-gapped or zero data retention environments, which is usually reserved for finance or healthcare.
Right.
But the most critical insight from the author is that banning AI outright is the most dangerous policy a company can implement.
Oh, totally. Because prohibition just drives the behavior underground. You don't actually eliminate AI usage. You just spawn shadow AI.
Yep.
Engineers are inevitably going to use their personal accounts. They'll paste proprietary corporate code into consumer web portals just to get their jobs done faster.
And suddenly, you're exposing the company's intellectual property to external training sets. Management teams often believe they are eliminating risk by blocking the tools, when in reality, they're maximizing it by losing all visibility.
Security has to be centered around active governance.
Right. And that governance is vital because of this terrifying new supply chain threat highlighted in the Qiita sources called slop squatting.
Slop squatting, that sounds gross. What is that?
It's when attackers exploit the way AI coding assistants hallucinate.
Okay, so hallucinations meaning when the AI just makes things up confidently?
Exactly. LLMs are advanced probabilistic engines. If you ask an AI to write a script for a highly specific task, and it doesn't have a perfectly matching library in its training data, it won't just admit defeat.
It guesses.
It uses token prediction to guess what a library doing that job ought to be called, based on standard naming conventions. It invents a phantom package.
Oh man. So attackers have automated the process of monitoring these models to see what phantom packages they hallucinate most often. When they identify a common hallucination, the attackers go to real package managers, like NPM for Node or PyPI for Python, register that fake name, and upload a payload of malware.
It's incredibly clever and incredibly dangerous.
The stats on this are staggering. The research shows that 5.2% of commercial AI suggestions and an alarming 21.7% of open source AI suggestions contain non-existent packages.
Almost a quarter.
Yeah. It operates like a GPS system, confidently directing you to drive across a bridge that doesn't exist. But a malicious actor anticipated the GPS error, went out and built a fake booby-trapped bridge over the river just to compromise your car when you follow the directions.
That is a perfect analogy.
So how do developers defend against a tool that just fabricates dependencies?
Defense requires leaning heavily into level 2 security concepts. First, you implement technical guardrails through strict content exclusion. Basically, you configure your dev environment to physically block .env files, API keys, and credentials from ever entering the AI's context window.
So the AI can't leak what it can't see.
Exactly. Second, you institute mandatory human-in-the-loop verification. You have to treat the AI exactly like a highly eager but occasionally careless junior developer.
Right, you'd never just push their code to production blindly.
Never. You never execute a dependency installation command generated by an AI without manually verifying the package's registry, its maintainers, and its download history. This is essential reading for DevSecOps teams or any tech lead trying to write an AI policy.
Okay, so once you establish that secure perimeter, the challenge shifts to productivity. Because if you're watching the AI like a hawk to prevent malware, how do you allow it to execute complex workflows without stalling out?
Right, because the standard failure mode for AI agents happens during prolonged tasks.
Yeah, and one of the most fascinating sources we have details the methodology for building a parallel loop coding agent using Claude Code.
So what happens usually is you assign a major feature, the AI generates 3 files, its context window gets totally bogged down with its own output, it loses the thread of the instructions, and it just stops.
It just gives up.
Yeah.
So the author solves this by using test-driven development, or TDD, but not just as a testing framework, as a mechanical kill switch for the AI.
Oh, that's interesting.
Right. Developers already know TDD, but here it serves a unique architectural purpose. The AI isn't allowed to decide when a feature is complete based on text generation. It's only finished when the test suite passes.
They combine this with the goal command, right?
Yep. Forcing the AI to loop continuously until the terminal outputs green.
But wait, a continuous loop introduces a massive token economy problem.
Because it's reading the whole code base over and over.
Yeah. If you allow an agent to loop endlessly while holding the entire codebase in its memory, it will consume hundreds of thousands of tokens. It incurs massive API costs and rapidly degrades the model's reasoning capabilities.
Okay, so this is where the parallel execution and context management come into play. The developer architected a system that heavily restricts the context window. They place only the absolute core rules in a root clau.md file.
Immutable directives like never delete a test to force a pass.
Exactly. And then they dynamically load specific skills on demand.
So, meaning if the agent is writing a front-end component, it only loads the React template skills.
Yep, it intentionally withholds the back-end database schemas.
That's smart. By strictly partitioning the context, the agent can spawn parallel subtasks, like drafting a database migration while separately linting a UI element, without the context bleeding into each other and causing hallucinations.
So you're basically trading the open-ended, conversational nature of an LLM for a strict, deterministic workflow.
It sounds like managing an AI agent is exactly like managing a team of easily distracted junior developers. You give them a rigid spec, a mechanical test to prove completion, and you actively hide any documentation they don't immediately need so they stay entirely focused.
Yeah, you force the AI to operate within the bounds of sound architectural design, which is critical because without rigid architecture, code bases naturally decay.
Oh, absolutely. And that decay applies to human developers just as much as AI agents. Without strict rules, humans write terrible code that solidifies into what the industry calls anti-patterns.
Yes. Our next source explores the poetic, almost dramatic names developers assign to these software disasters.
The terminology perfectly encapsulates the pain of dealing with legacy systems.
It really does. So the first major anti-pattern highlighted is lava flow.
Lava flow. I love that word.
It describes dead code or temporary workarounds that have hardened into the production system.
Right. The original author probably left the company years ago, and the current engineering team is too afraid to delete the code because they have no idea what dependencies might break. It just solidifies.
Lava flow is particularly dangerous because it acts as an anchor for future technical debt. Since developers are terrified of modifying the hardened code, they build new, equally convoluted workarounds layered on top of it.
The architecture just gets increasingly brittle over time.
Another classic is cargo cult programming. This happens when a developer copies code, whether from Stack Overflow or an AI generation, without understanding the underlying mechanics of why it works.
They just paste it in like a magical incantation.
Exactly.
The origin of that term is fascinating, actually. It stems from post-World War II Pacific Islanders who built mock airstrips out of wood, hoping to summon the cargo planes that dropped supplies during the war.
Oh, wow.
Yeah, they perfectly replicated the outward form of the runway, but completely lacked an understanding of the underlying mechanics of air traffic control and logistics.
That is wild.
Right. So when developers do this, they introduce code that happens to execute successfully today, but fails catastrophically during an edge case tomorrow because the core logic was never actually grasped.
And speaking of catastrophic edge cases, the article highlights the magic string anti-pattern.
Oh boy.
This occurs when a developer hardcodes a specific string of text to trigger a hidden feature or denote a null value, assuming no user will ever naturally input that exact string.
Which is always a bad assumption.
Always. The real-world example provided is legendary. A man requested a vanity license plate for his car that literally read NO space PLATE.
No plate. A seemingly harmless joke.
Right, but it interacted terribly with legacy database schemas. Across the entire state, whenever police officers issued a parking ticket for a vehicle that lacked a physical license tag, standard procedure dictated they write no plate into the terminal.
Oh, I see where this is going.
The municipal database didn't recognize this as a null value. It recognized it as a magic string. Because this guy legally registered that exact string, the system assigned every untagged parking violation in the state to his vehicle.
Oh my God.
He received thousands of citations.
That is the ultimate cautionary tale regarding predictable environments. You can never assume user input or legacy system behavior will conform to the likely scenario.
Never.
Relying on magic strings instead of enforcing strict data constraints pretty much guarantees an eventual system failure.
Oh.
Any junior dev listening to this, take note. Don't write magic strings.
Seriously. So if the antidote to magic strings is strict constraints, what is the antidote to cargo cult programming? How do we ensure developers and the AI agents they manage are actually engineering reliable systems instead of just blindly pasting code?
The only permanent defense against code decay is a fundamental understanding of the core concepts we rely on. We have to understand the underlying mechanism, not just the surface-level syntax.
And our final Qiita source tackles this directly by clarifying 3 foundational programming terms that dictate system architecture.
Safe, pure, and idempotent.
Misunderstanding these concepts is how massive bugs get shipped to production.
Absolutely. So in the context of API design and function architecture, safe simply means the operation does not alter the target resource. It is entirely read-only.
Okay, so to ground that in everyday experience, a safe operation is like reading a restaurant menu. You can read the menu all you want, but observing the options doesn't change the ingredients cooking in the kitchen.
Exactly. The state doesn't change. The next concept is pure. A pure function has absolutely zero side effects. It does not modify global state, it does not rely on external variables, and it always returns the exact same output for the exact same input.
Okay, so a pocket calculator operates as a pure system. If you input 5 plus 5, it will always evaluate to 10. It performs the computation flawlessly, but it doesn't send an email, it doesn't log the keystrokes to a cloud database, and it doesn't alter the physical environment.
Right, it just computes and returns the value.
Got it.
That brings us to the most complex of the three, idempotent. An idempotent operation can be executed multiple times in a row, but the final state of the system remains exactly the same as if it were only executed once.
Okay, so idempotency is like pressing the call button for an elevator. You press it once, the circuit closes, the button illuminates, and the elevator is summoned. If you impatiently mash the button 10 more times...
Like we all do.
Right. The system doesn't summon 10 elevators, nor does the car arrive any faster. The end state of the system, the elevator is in transit, remains perfectly identical regardless of the repeated inputs.
That's a great way to think about it. But the nuance that trips up a lot of engineers is the distinction between pure and idempotent.
Wait, how so?
Well, consider a mathematical function that adds 1 to a given number, we'll call it increment. Is increment pure? Yes. You pass it a 5, it evaluates to 6 with no side effects.
Right.
But is it idempotent? No. Because if you run increment twice on the state of 5, the first run yields 6 and the second run yields 7. The system state changed upon repetition.
Oh, okay, I see.
Conversely, taking the absolute value of a number abs is both pure and idempotent. The absolute value of -5 is 5. If you apply the absolute value function to that result again, it remains 5. The state stabilizes immediately.
Wow, understanding that distinction is critical for network reliability.
Oh, completely.
If an engineer knows a specific API endpoint handling a financial transaction is designed to be idempotent, they know the system can safely retry a dropped network request without the risk of charging a customer's credit card twice.
It moves the engineer from just writing syntax to architecting resilient infrastructure. And honestly, this is a must-read for any back-end engineer building APIs. The tools we use to write code are evolving at breakneck speed, but the foundational logic required to engineer stable systems remains entirely unchanged.
It's been a massive journey through the sources today. We started by exploring the futility of trying to outsmart modern compilers with 12-hour bitwise operations.
Yeah, RIP to that developer's weekend.
Seriously. Then we looked at the counterintuitive hardware strategy of offloading AI experts to the CPU to free up memory bandwidth and triple generation speeds.
We analyzed the enterprise threat of slop squatting and the necessity of strict governance.
We examined how to wrangle AI agents using test-driven loops and isolated context management. And finally, we explored how human anti-patterns like lava flows and magic strings can only be defeated by returning to the core architectural principles of safe, pure, and idempotent systems.
As automation assumes more of the mechanical burden of writing code, the value of an engineer shifts entirely towards system design and architectural governance. Apply these mental models to your own work.
Definitely. And that leaves us with a lingering thought for you to consider. As AI inevitably takes over the generation of our boilerplate code and functional syntax, will the human ability to spot a lava flow or mathematically define idempotency become a forgotten ancient art? Or will a deep structural understanding of those fundamentals become the singular skill that separates a true engineer from the machines?
It is definitely something to keep in mind the next time you find yourself looking for a secret shortcut, whether you're navigating rush hour traffic or architecting your next deployment.
Exactly. Don't forget to subscribe and like. We've got a new episode of Dev Trends on the Go dropping tomorrow. Have a great day and happy coding.